I will not again answer the same question that I asked in the first course, but the idea of this second lecture is a bit more prospective, while the first one was a bit historical. That one is more about, well, basically, we can imagine, we can guess that in the next few decades, we should be able to detect something which will be like evidence of life outside the solar system. Maybe we won't detect, but at least we will have the instrumentation that will allow us to detect life on another planet. So the objective of this course is trying to see, okay, within the next few decades, what are we expected to do? What kind of signal we are expecting to detect given the instrumentation that we are doing, and trying to anticipate what kind of data, what kind of information we will have to then search, well, on the planet, to then search for life on another planet. So that's basically the requirement we have if we want to search for life on another planet in the universe, and that's basically the roadmap of exoplanets for the next decades, few decades. We first need to detect a planet that will have suitable conditions to host life. And that's not an easy question to answer because they are, well, this term is easy, but this part, what are the suitable conditions to host life? I think no one really knows. Well, we know the life on Earth. We know I think we can pretty well know what are the conditions for life on Earth to emerge, but we don't know if there are any exotic life or what are the conditions we need for those. But anyway, at least we need to have a planet for those life to evolve and to emerge. And then, because we won't be able to probe in situ the planets, the number I'm using when I'm doing outreach talk that I mentioned in the first lecture about Proxima Centauri b, the exoplanet next door, it is a rocky planet, like a rocky planet in the habitable zone of the closest star to the sun. If we want to go, send a spacecraft to probe the atmosphere of Proxima Centauri b, and we send a probe that is going to the same speed as the Voyager 1 mission, which is currently the spacecraft launched by humankind that is going the fastest as we can, 61,000 kilometers per hour. We need 70,000 years to reach Proxima Centauri. So again, that's outside a PhD project by a lot. So we basically can't unless we do several breakthroughs in technology and we can do like sci-fi movies. We will have to probe those planets remotely from the Earth or at least from space. So the second thing we do need to do is to probe their atmosphere remotely to search for biomarkers. So those are the two requirements if we want to search to detect life on another planet. We first need to detect the planet, and then we need to probe its atmosphere and search for biomarkers. So in the near future, well, it's really near, we have one of the main missions that will fly in the near future that will have the capability. Well, I'm just going for the first point now to detect the planet. We saw in the first lecture that we basically have still no Earth analogs. We have some planets that are in the habitable zone of something like sun-like stars, but they are way too far. Those two Kepler targets I mentioned in the first lecture are way too far, way too faint. The stars are too faint. We can't detect their atmospheres because the star is too far and too faint. So if we want to probe the atmosphere of those planets, we need to find Earth analogs, planets in the habitable zone of sun-like stars, but on bright stars, because we need to have a lot of photons to probe their atmospheres and so on. So that's why we designed it a decade ago. Well, it was proposed a decade ago the mission called PLATO, and because we are among us, even if Big Brother is looking at me, Plato, given what I said in the first lecture, we should have called Plato Epicurus instead of Plato, right? Because Plato was claiming that there was only the Earth, and that there is no other Earth, other planet in the universe. Well, unlike Epicurus, who were claiming there was an infinite amount of world. And PLATO is a mission that is designed to find planets, unlike what Plato was saying 2,000 years ago. Anyway, so this is a mission from the European Space Agency. It will be launched in December 2026. And the top mission objective of PLATO is to detect Earth analog, full stop, around bright stars, for which we will be able then to probe the atmosphere, because the stars are bright enough and the objects are relatively close, relatively nearby, so then we can then detect the atmosphere. Something we could not do from Kepler because the targets were too faint. And we don't want only to detect Earth analogs, we also want to characterize them in terms of mass, radius, and age precisely and accurately. And the requirement that we have is that we want to detect the mass, well, first the radius with a precision better than 3%. We want to detect the mass. Of course, PLATO will not detect the mass, but it will detect, we will need to use the radial velocity method complementary to the transit method here to detect the mass, and we want to do that with a precision better than 10%. And we will also we also want to get the mass, the ages of those systems with a precision better than 10% in order to have, well, the mass and the radius is to have the density and the composition, to then derive the composition with a really good precision, to then be able to disentangle between a rocky planet, a water world, a gaseous planet. And the age, this is not coming from this is coming from the stellar physics that is important for the mission as well. And the age is to understand the evolution of the planet, because of course planets evolve on their lifetime, and knowing the age is something which is something important. And so PLATO is focusing, the main objective of PLATO is really to focus to find planets that are in the habitable zone of sun-like stars, not on M dwarfs, and the mission is not designed to probe M dwarfs. And you've seen this, probably this plot with the habitable zone, and this is the tidally locked radius. So all the planets which are within this region are likely to be tidally locked, meaning one face facing the star, one face never seeing the star. And you see that the habitable zone of M dwarfs, basically, they are all supposed to be tidally locked, if they are circular. Of course, if they are eccentricity, it makes it a bit complicated, but anyway. So we are focusing on those planets, basically, around K or G, or even for F stars, where we should be able to detect, we will be able to detect with PLATO, transiting planet there. Just to give you some updates about the mission, because I'm quite involved in that mission. So it's actually not a small mission, as you can see here. This is human. This is the flight model of the optical bench, where we will install on this optical bench 26 small cameras, each of them being 12 centimeters in diameter. And you have pictures of the 10 first flight models of the flight version of the cameras that are already been delivered to the prime, to the industry that will implement them into this optical bench. And the idea of PLATO is to, well, I told you at the beginning that we have a relatively low transit probability. So if you want to detect Earth's analogs, we need to observe a lot of stars. And if we want to observe a lot of bright stars, there are not that many bright stars in the sky. We need to have a large field of view. And if you want to have a large field of view, you need to have an optical design, which is based on optical lenses like this. But you can't make a large aperture optical lens, otherwise the weight of this will be huge, and the rocket will probably not lift off. So the smart approach does say, like, okay, we need a large field of view, so let's make small, large aperture telescope cameras, and just put as many as we can, to compensate the fact that each of them will have a relatively low precision because the aperture is small. But if we have many, well, we compensate the fact that the aperture is small by having more. And in total, we will have 24 plus 2, 24 cameras that will be on the payload, and that will look at the same stars for several years, just like Kepler did at that time. And we will have the precision with PLATO to actually detect Earth analogs. And we make some computation just last week, who claim that even an Earth planet slightly bigger than the Earth will be detected. Each individual transit will be detected on a sun-like star, even considering all the noise properties of the stars. So this is the first 10 flight cameras. Of course, the cover will be removed before its flight. And something we did for PLATO is that we name each of the camera after famous astronomers, and because there are different countries, each country's suggested names. And for France, it's Françoise Praderie, who was an astronomer at the Paris Observatory and make a great development in stellar physics. And the Françoise Praderie camera is already ready. And I think we have in France a second camera. It will be named after André Baran, who was the designer of the LOD spectrograph that allowed the 51-peg discovery. So we are currently producing, testing, validating, qualifying 1 camera per month, which is a bit crazy for the people doing the hard work actually and doing the test in the vacuum chamber and so on, to produce 1 camera per month. This is a bit crazy, but we are on track. It will be launched. It is planned to be launched in December 2026, and everything is still green. We have no delay, and it will be on board Ariane 6. And we are expecting the first public release. Basically all the light curve, all the stars. We will be observing 160,000 stars simultaneously for several years, with a cadence of 25 seconds continuously. So it's a huge amount of data. And all those stars, but 2,000, will be released to the public as it goes. The 2,000 are just proprietary to the consortium. But most of the data will be public, and you will be able to play with those light curves, something like by the end of 2028, maybe 2029, if we get some delay for any reason. So this is the last update of the mission. We have another instrument. So that is for the transit, and so PLATO will have the capability to detect Earth analog. We designed the mission for that, and everything is on track. Everything is compliant with the requirement. So we will have the capability, the detection to detect Earth analogs. Now, from the ground, for the radial velocity, we have an instrument that is already on sky, which is called Espresso. That is linked to any of the 4 telescopes in Chile called the VLT, which each of them is a 8-meter telescope. Let's do the movie again. And the Espresso instrument, this is a high-resolution, ultra-stable Herschel spectrograph in the visible. For those of you who are aware of that, can be linked to any of the VLT, or can actually be linked to the 4 of them, to have equivalent of 16-meter class telescope. It has a radial velocity stability down to 10 centimeters per second, so it should have the detection capability to detect an Earth analog. And it's already running in Chile, and the PLATO field of view will, the first field of view of PLATO that we selected will be visible from Espresso. We make sure that Espresso will be observing the PLATO field. And so we are expecting the pair of Espresso and PLATO to be able to detect by, let's say, the end of this decade or early next decade, and for Earth analogs, both in transit and in radial velocities, on bright stars. When I was doing my PhD about 15 years ago from now, I was not here, but I could have came actually to the Red School. I should. I was doing this plot. It was quite famous at that time, about the radial velocity amplitude of signal we detected across time. A bit like the movie I showed you before, but this is in time. And basically, when I was doing my PhD, I was saying like, hey, there is kind of a slope here, and we are improving in time with kind of a constant improvement, the detection of small planets. And at that time, I was saying like, okay, well, we should be detecting the first Earth analog in radial velocity by 2025, 2024, meaning now. But no, that was not a good prediction. something happened in something like in 2010 when we start to have radiology spectrograph that were good enough to probe this regime here below 1 meter per second. We have the instruments that are good enough for that, but we don't find planets. It's not because there is no planet below 1 meter per second, because of course the Earth is actually one of them. It's because there is a kind of a noise floor in terms of radial velocity precision where we can't reach below because stars are variable. And the stellar variability, we are observing stars, we are observing the planet by the indirect methods, by looking at the stellar light and seeing the stellar variation in the profile of the stellar lines. And because the stars are not perfectly constant in time and perfectly uniform, the variability at the surface of the star impact the detection of the measurement of the radial velocity. And this creates this noise floor that we reached starting like 15 years ago in radial velocity, and we have basically no detection below 1 meter per second. Although we have the instrumentation like Espresso now, which is actually operating for about 5 years now, that is capable to go much below 1 meter per second. The reason for that, this is what we call the stellar variability, and this is definitely the challenge for this decade, is that stars are variable. And this is an experiment that is running actually for probably 10 years now almost. This is several years, I think 3 years of observation of the sun, observed with ARPS North, one of the spectrograph like ARPS, but in La Palma. So a high resolution, high precision spectrograph that is stable much below 1 meter per second, every day for more than 10 years. And the sun observed as a star. So they basically scramble all the light from the sun, not resolving the surface, to make sure that we observe the sun just like it was a star. Well, the sun is a star, but like we are observing the stars. And basically, this is the observation in blue. And you see that you have a scatter here at the level of a few meters per second. And the red curve here, this is the expected signal of an Earth-like planet in radial velocity. So the challenge we are facing now, it's not an instrumental issue, because the instrument, no, it's not the case for ARPS North, but Espresso will do the same. And actually we are building we have some colleagues in Portugal who are building a concept, a small instrument that will send the flux of the sun to Espresso, so then we can do the same thing, but with Espresso. Anyway, we have the instrumental capability to detect the red curve, but we observe the blue points. And the challenge we have now is a data science issue, is a statistical issue about how can we actually remove this noise, which is caused by stellar variability, to actually be able to narrow down the scatter of the stars down to be able to measure these kind of things. And the reason for why the sun, which is actually quite a quiet star, shows kind of large variability at the level of a few meters per second, much above the target amplitude for a sun, for an Earth, you have two main effects. First of all, you have features at the surface of the sun and of stars as well, like star spots, which are not, now we know they are not windows from the inhabitants inside the planet, inside the sun, sorry. So those star spots, when you observe the photosphere of the star, and you have a line profile here, because of Anna's talk, I guess you know pretty well all those lines form. And when you have a dark region going in front of the stellar surface, this is deforming, perturbating the stellar line. And when you measure the radial velocity, you are measuring the barycenter of this line. So when the spot is going on the stellar surface, you basically have a shift in radial velocity, just because the spot is crossing. And if you go back to this slide, and if you do the parallelogram or the Fourier transform of this, you will find 30 days, which is the rotation period of the sun. So this can be clearly explained. We understand this. The problem is that we don't resolve the surface of stars. Only the sun we can resolve its surface, or sun-like stars. We can resolve some very giant stars. We can resolve them, but for sun-like stars, we can't resolve their surface. So we don't know where spots are. We don't know even if they are spots or if they are plages or facules or whatever. The surface of the stars are completely unresolved. But we do see some shift in the line profile due to these effects, and we have trouble to remove that from the data in order to correct for this effect. Another issue we have is that this is real observations of the surface of the sun, of course not of a star, and what we see is like when you boil water for pasta, you have kind of bubbles coming out, and these bubbles, this is just plasma, and the hot plasma is the bright spot here. This is hot plasma getting out of the star, and because it's getting out of the star, it's blue shifted a little bit, and it's bright because it's hot. And then you have some darker area around the bubbles there, which are this is plasma going down falling into the star. So this is red shifted and cold, and less bright, and that you can see it clearly here. So basically, when you look at the stars, because of granulation, the granulation make the star slightly blue shifted because of all this plasma getting out, being brighter than the red shifted part of the plasma going down. But this is fine because in average, the granulation is averaging out, and you just have a small blue shift because of the granulation that is averaging out on the surface of the star. So it's just a shift, an offset. But when you have features at the surface of the star, you are removing locally the granulation. And it means you are inhibiting this blue shift of the star locally. And this creates variation that is linked to the rotation of the star, that is creating some radial velocity variation that are actually even stronger than what we are seeing here. And on top of that, this granulation is not actually completely averaging out. It's averaging out over a long time scale, but it has some time scale still. That is the time scale of the granulation. And if you look at the time frequency of these bubbles, you can see there is kind of a cycle. And within this cycle, we can see some variation because of the granulation, which is at the level of maybe 1 meter per second, maybe a bit less in case of the sun, 0.8 meter per second. If we want to detect an Earth analog in radial velocity, well, we have already espresso. Espresso is an exquisite instrument. It's completely unbelievable how great this instrument is. It's not a problem of the instrument. It's a problem of stellar physics and of the way we are doing the statistical methods to correct. And so we have an issue, we have a challenge that we are facing, and we really are working hard. There are a lot of people in the community that are trying to solve this challenge of the stellar variability in radial velocity. We hope we are working at least to solve that issue by the time PLATO is launched, and we have actually started a new working group within PLATO consortium to try to answer that question, at least for PLATO follow-up, in order to be able to detect Earth mass planet in radial velocity, even if when they transit. This is the roadmap of exoplanets in space. I already mentioned some of those missions in the past. I mentioned about CoRoT, I mentioned about Kepler and the K2 extended mission. Because at some point in 2013, actually we lost CoRoT, and the same month we lost Kepler as well. And we lost Kepler because the space, well, when you're mission in space, you need to be stabilized. And if you want to get a very precise and stable photometry, you need to have a telescope in space that is extremely stabilized, and the pointing is really fine, is really precise. And for that, you have reaction wheels on the telescope that correct for any perturbation on the spacecraft. One of the main perturbations on the spacecraft is the solar pressure that is unbalanced on the design of the telescope that make the telescope to rotate. And reaction wheels are there to correct for this perturbation. And there were 4 reaction wheels on Kepler, but after a month or two, a few months, one of the reaction wheels, you need 3 reaction wheels to correct for the three angles. So there was one backup, and the backup, one of the reaction wheels actually failed after a few months. So that's fine. There was a backup. There was only 3, and Kepler lasts for 4 years, 4.5 years, using 3 reaction wheels out of 3. That's fine. But in May 2013, the second reaction wheel start to fail, and so with 2 reaction wheels, you cannot compensate the three axes. And so the engineer at NASA, they found that if you put the telescope on the ecliptic, the telescope is kind of symmetric toward the solar pressure, and so it balances on the both sides, and you can point the telescope quite precisely just with 2 reaction wheels. And that's why we stop the Kepler prime mission. We stop observing the same stars, and we move to the K2 mission that was pointing on the ecliptic for shorter duration, but we increase the number of targets, and we have a new mission based on the Kepler telescope that was operating until 2018, when actually the telescope Kepler itself became too far away from Earth to be able to use it, because it was just too far, and the communication was not good enough. There was not enough bandpass to communicate with the telescope. In the past, we also have the Hubble Space Telescope and the Spitzer Telescope that were not much used. Well, I should not say that with Elsa in front of me. Sorry. But those missions were mostly used and for characterization of the atmospheres of the planet. But Spitzer was used to detect how much? 5 of the TRAPPIST-1 planets? 4. Yeah.
To kind of solve the period.
Yeah, sure. But from the ground there was 2, 3, 3 from the ground, and 4 more from Spitzer. So actually Spitzer detected some planets, in some interesting ones actually, from TRAPPIST. In 2013 there was the Gaia mission. I mentioned Gaia because it was during the question about the astrometric part, and Gaia is expected to deliver next year, or to 2026 maybe, the full catalog of astrometry of stars, and from which we expect to detect several thousands of tens of thousands, we don't know, of planets using the astrometry method. Then in 2018, basically a few months after, before we lost completely Kepler, there was a test mission. I mentioned the test mission as well during the question, because it has a kind of the same instrumental design as PLATO. 4 cameras pointing to different positions of the sky, and basically TESS is scanning the sky, is doing a full sky survey of stars in photometry, and it has 4 cameras pointing with the 90 degrees field of view basically, and scanning the sky like this with 27 days of observing campaign. So basically the light curve you have from TESS are just for 27 days, and then you move to other stars, except if you are near the ecliptic pole, then you have more observation. But most of the stars are being observed for only 27 days. Then in 2019, we launched CoRoT. CoRoT is a small mission from ESA. With the initial objective was to try to catch the transit of stars, of planets being discovered initially by radial velocity. But actually, quite a lot of them actually were already detected by TESS. Probably you heard about this thing. Did you? Called GWST, and is doing. I mean, this is another impressive machinery that is doing a lot of things to probe the atmospheres of exoplanet through transmission spectroscopy, and this is completely great mission. I just mentioned about PLATO, sorry, and we have in the near future we have another 2 missions that will be launched. Roman Space Telescope, which will have the first instrument in space to detect the reflected light of exoplanets by directly imaging them. And we are doing the direct imaging stuff already from the ground, but on young stars, on young planets, because they are, as I said earlier, because they are young, they are still hot, and the contrast in the near-infrared is good enough. But if you want to detect relatively old planets by their reflected light, you need to have a contrast of 10 to the minus 10 to the 10. And that's a huge contrast, and you can do that only from space. And the Roman Space Telescope will have the first instrument, actually it's a demonstrator, to be able to detect first exoplanets through their reflected light. So we will be able to probe planets that are probably far away from their star, but old, not only the young planets. And then we have Ariel. If you want to learn more about Ariel, ask Martin about that. It's a mission that will do the atmosphere of exoplanets, but focusing on giant planets mainly. So we have some instruments, and this is only for the space part, because we also have ground-based observatory, and we have a lot of ground-based observatories with either radial velocity spectrograph or spectrograph that can, for either for radial velocity or for transmission spectroscopy, or both, that are everywhere on Earth, that are actually one of their scientific interest and scientific goal is to actually study exoplanets. So it's like we have a lot of data to analyze, and that's why also we need a lot of people to analyze all this data. So that's actually what I mentioned, is probing the atmosphere of exoplanets. GWST already started, put 2022, but actually it was launched in 2021, but it started in 2022. And GWST basically doesn't have the capability, the instrument is too small to detect the atmosphere of an Earth analog, meaning an Earth-sized planet in the habitable zone of a Sun-like star. Unless you dedicate something like half of the time of GWST for the next decades, but that's not possible. So GWST is still not enough to detect the atmosphere of an Earth analog. Ariel is not designed at all to do that neither. Ariel is a mission that will do a survey of about 1,000 gaseous planets to probe the diversity of planetary atmospheres for giant one. But that's a very important mission, because we need to understand, well, we need to know how to walk before learning how to walk, or to run. And if we want to study the atmospheres of Earth analogs, we need to start with something that is a bit easier. And what is a bit easier is probing the giant planet atmospheres. And that's actually what the Ariel mission that will be launched in 2029 or maybe 2030, that what it will do, it will probe a lot of planets, giant planets, trying to understand the diversity in the atmospheres of giant planets. And from that, we will probably improve a bit the modeling as well of this atmospheres spectra. And from that, that's an important step if we want to go then to explore the smaller planet and the Earth-sized planet. As I already mentioned, the Roman Space Telescope, from space, it will be able to directly image the reflected light of exoplanets that was supposed to be launched 2026. If everything goes well, and well, it's already on good tracks as well, and all the optics have been delivered already, and the instrument seems to be working fine. So we should be able to detect the first exoplanets with their reflected light, and not only young exoplanets. From the ground, we are working on this huge thing that is called the extremely large telescope. After the very large, we have the extremely large, and then we have already foreseen about the overwhelmingly large telescope, but this is still a project. We have chosen some people who are thinking about doing an overwhelmingly large telescope on the moon, but that's probably still sci-fi for39 So this telescope is not sci-fi at all. This is actually being built in Chile. This is a 39 meter in diameter. So you take this room. It's not enough to put the mirrors of the ELT inside this room. The building itself, the dome here, is 80 meters in diameter. So from here to the other part of the lake, basically. That's the size of the dome. It's not well, we have the chuck here to scale. Okay, that's a big thing, and we will have also some instrumentation that will be dedicated and designed to do the high resolution imaging and to directly image planets. But because of the atmospheres on top of us, we will only be able to do the thermal emission, which is already be great because at this diameter, we should be able to probe much closer to the inside the star that we were able to do before. And because of the large aperture, we will have a huge amount of flux. So we should be able to probe probably fainter targets, fainter planets, and so lower mass than what we have done so far. And this, I mean, like this is coming after tomorrow. I mean, like 2026, you probably finish your PhD, most of you by then, or just you will probably be writing your PhD thesis. Sorry for that. Sorry to remind you that. When those instruments will be launched. But that's great because once you are defended, you can have a postdoc, working on those instruments, and that's great. And then we already foreseen, I mean, like both NASA and ESA, the European and the American Space Agency have already made their roadmap already at the end of the 2010s decade, before the 2020, about basically they say, okay, we want to do flagship mission, large mission, ambitious mission for, let's say, 2040, 2050. And they basically ask the community, expert panels, and so on to meet and to discuss what we should do as an ambitious, big flagship mission by the mid of this century. And what came out clearly out of the NASA Astro 2020 decanal discussion was this guy, which now called HWU for Habitable World Observatory. Do you want me to explain what is aim, or this is clear enough? The objective of this is to do the direct imaging of Earth analogs, meaning stars, planets around nearby stars, and to directly image them in reflected light. And because we will be able to, when you resolve a planet, you can put a spectrograph on that, and you get a spectrum of the atmospheres. And then from the spectrum of the atmosphere, you can try to see if there are any biomarker in that. It will be working in the relatively near infrared. It depends what your definition of near infrared, but it will be relatively near infrared. That's basically slightly bigger. The design is for something that is slightly bigger than GWST, but not completely large. There was the design at the beginning of a 15-meter class telescope, but the problem is that it was difficult to imagine putting that telescope into one rocket and to make sure that it can be deployed and so on. And this was, in terms of budget, that was completely crazy. And so they end up with this design of an off-axis telescope of something like 7-meter telescope. It depends on what your definition, if you take this part of this outer part anyway. It's about like the size of GWST, slightly bigger, but with a much better design for the direct imaging of exoplanets, much better than one GWST is doing now. And if you have already looked at the GWST pictures that are completely amazing and great, you see that stars are not like point source. They have like this kind of round thing in front of the stars, which are due to the design of the instrument. But this is a kind of a nightmare if you want to go very deep and very close to the star. So this off-axis there make the pupil of the instrument almost perfect, and you can go much deeper and much closer into the stars, and with the enough precision and enough contrast to actually be able to detect Earth analogs around nearby stars. When I say nearby, I say less than 20 parsec, so less than 60, 70 light years. And in Europe, we made our own committee as well, and our own prospective work, and we came up with 3 different large missions for ESA. One is to go back to the giant planet in the solar system. One is to explore the universe in the gravitational wave, and another large mission is the objective is to probe the atmosphere of temperate planets, with one mission concept that was suggested at that time, which is life. Again, the wording is quite meaningful. It's actually meaning it's actually for large interferometer for exoplanets. And the objective of this, the concept of this mission, is not to send just one telescope, but to send 3 up to 4 small, relatively small telescopes that will make the aperture, equivalent aperture of a much larger telescope. And we can put them at a different position to change the aperture, to change the diameter of your telescope. And then recombine the light into a fifth spacecraft here that will be doing what we call the Newling interferometry. So basically, it will use the interferometry of the star with itself. And so it will use the interferometry properties to remove the stellar light while preserving or even boosting the light from the planet. We are actually doing that from the ground with the instrument called Gravity on the VLT. And the idea is to do that from space in the infrared with this instrument called LIFE. And that is expected to be launched something like 2050, but there is no clear commitment from my side on the launch date of this at all. And again, this instrument will be focusing on planets up to 20 parsec. And the smart approach of this European concept is that you can change. I've told you in the previous lecture that the angular resolution you can get is something like 1.22 lambda, the wavelength over the diameter. And that's scale at a given distance of the star to a given separation. So if you separate if you move the spacecraft away by the right distance, you can make sure that your instrument, the equivalent diameter of your instrument, can resolve the habitable zone of the stars regardless of their distance. And the further out the stars are, you can make the spacecraft the larger out, further away, to probe the habitable zone. If you have a very close-by star, nearby star, you can make the spacecraft to be closer to each other, and you can still probe the habitable zone. Of course, it seems easy, like I said. It's a bit more technically, because the flight formation of spacecraft like that at this precision is not straightforward at all. But we are working on that, and we have a team in Europe that is quite active in order to make this concept true, and being able to probe the atmosphere of temperate planet, meaning the atmosphere of terrestrial planet in their habitable zone. Those two missions are not in competition at all, because they will be observing 2 different wavelength bandpaths. And actually, we know now that if we have an Earth analog, really like a clone of the Earth on another star, any of those two individually will be able to detect all the biomarkers that we could detect on Earth, because their wavelength range is not enough. Each of them will not be able to detect all the biomarkers. But both together will be able to detect all the biomarkers that could be detected on the Earth. And so we anticipate that having 2 missions, one from NASA and one from Europe, from ESA, will be able to probe the atmosphere of terrestrial planets in order to detect biomarkers. And if there are biomarkers and life on the planet, we should be able to detect it, thanks to the complementarity of those 2 missions. In the remaining time, I wanted to do an exercise together and try to be ahead of time. I realized that when I prepared this lecture that 15 years ago, I was at your position, I was doing my PhD. So now, imagine that we are no longer in 2024, but we are in 2039. I'm not doing the talk. You are on my position now, and you are doing the review talk about exoplanet in 2039 at the red school number, whatever. You will probably still be there in 15 years from now. And let's try to guess, to imagine, to project what we will have in 15 years ahead of time. Of course, this is completely ignoring the threats of climate change on research And this is assuming that the business is as usual and we can continue like we did for the last decade, and there will be no impact of whatever I'm going to present from the climate change. Another important disclaimer that this is definitely my own personal guess, of course. I don't have a crystal ball and I cannot predict future, but we will try to discuss together what we should expect from the current roadmap of exoplanet mission and project that we are foreseeing for the next 15 years. Trying to answer also those two questions, those two requirements I mentioned at the beginning. First, to detect an Earth analog, and then to try to characterize the atmosphere. So imagine that now we are in 2039. So I will speak in the past, of course, because I will mention about what was done in the last 15 years since 2024 to 2039. And so we can imagine that now we are in 2039, we have resolved the problem of stellar variability on radial velocity. This is no longer a problem. We solve it. No big deal. We understood it perfectly, and this is no longer a limitation. Fine. The old generation spectrograph, like Espresso, well, remember we are in 2039. Espresso was on sky in 2017. So it's operating for more than 20 years. This is the old generation spectrograph. It has produced a catalog of a few tens of Earth analogs within 20 parsec. We have targets, Earth analog, we know their mass. We only know their mass because we don't know if they are transiting. And we have several tens of Earth analogs within 20 parsec. Cool. The extended PLATO mission is reaching its completion. And we still need to do some radiology follow-up of a few systems because there are a lot of planets, outer planets, and we are still doing the, by 2029, I will still be doing some follow-up of PLATO targets, probably, yeah. And PLATO detected several tens of Earth analogs in transit. We discover them, and we characterize them precisely, exactly like we predicted we will do. But only a handful of them are transiting around very bright stars. But OK, that's actually what we expected back in 2024. And probably none of them is within 20 parsec. Maybe one, if we are lucky. But let's say none of them is 20 parsec. Remember that if we want to use LIFE and HWO, we need relatively nearby stars within 20 parsec, and the transit probability, if you take all the stars within 20 parsec, the transit probability, even if they all have an Earth analog, the transit probability to have is relatively low, and you don't expect to have, you expect to have 0 or 1 of those Earth analog within 20 parsec. So PLATO will discover a lot of Earth analog and characterize the mass and radius around bright stars, but very unlikely there will be one within 20 parsec that could fit the HW or LIFE future mission. The Gaia mission released the catalog of 10 to the power n. I don't want to put the value of n, but it's large enough, of new exoplanets. So it's a complete revolution. We have a lot of new giant planets to do statistics. It's completely crazy, amazing, great time. But none of them is expected to be okay because we know that the Gaia precision in terms of astrometry is not good enough to find planets that are below giant planets. So they are all too massive to be Earth analogs. The LT is now working smoothly after some time to understand all the 1,000 optical pieces to work together and so on. Well, we are 2039. The LT is working fine for quite some time now, but it has already started imaging young Neptune mass planets, much smaller in mass, lower in mass than the previous one we directly imagined before the ELT. The population is huge. But we have even more trouble to determine their mass because we don't have dynamical mass. We just infer the mass from their spectrum, and it's difficult to do that. The Roman Space Telescope was a great success, of course. We were able to detect reflected light of a few old giant exoplanets, and we are working on the instrument for HW, which was again postponed after the cut in budget of NASA by Voldemort. The Roman Space Telescope also has one part of its survey. I didn't mention it during the course in 2024, but one part of the project is actually to explore planets through the gravitational Michelin. I didn't mention it. And they discover something like 10 to the power m, m being large again. New exoplanets. Actually, some of them are relatively low mass, but none of them could be further studied because the gravitational microlensing happened only once, and you cannot study the signal again. So this is just to statistical studies. That would be completely great. No, that was completely great for statistical studies, but not for. We can't characterize and we can't study further those exoplanets. So now going to the atmosphere. So the aerial survey of atmosphere is over by 2039. This is great. There are so many spectra to interpret. This is completely crazy. The diversity in exoplanet atmospheres is huge, and the GCM, the global climate models, are far from being able to explain it. What are you doing, guy? Stop going to the beach. Ariel is the name of this girl. We are working on a new mission concept that we suggest to call Flounder. To probe the atmospheres of PLATO small exoplanets in transit, but the cosmologists, the solar system, and the high energy communities are complaining that we are suggesting again another exoplanet mission. But it's not our fault if we are doing an interesting science. And common stellar variability is still a main limitation to interpret the transmission spectrum of exoplanets. And because, I mean, like when you remove the light from the star go through the atmospheres of the planets, it brings with this the properties of the stellar variability, the features, and you can have detection of water in your atmospheres of exoplanet that is actually not water in the atmosphere, but kind of water in the stellar spots from the stars that you uncorrect and make a fake detection. But that's good that the RV experts that solve the RV issue in stellar variability, now they are joining our forces to understand the stellar variability. So we are more forces and more people now that are still working on the stellar variability, but no longer for the RV because they solve it, but to understand the impact of transmission spectroscopy for small planets. The GWC mission ended up too quickly. It was hit by Starman and Elon Rooster. We were so unlucky. But anyway, the mission was going to end anyway because the reaction wheels that were the same as for Kepler were not working fine, and even if there are 6, 3 of them end up well. And so we knew that the time. I mean, we are in 2039. Okay, GWC. Don't complain. GWC was launched for 5 years nominal mission, but okay, it was hit by Starman. There was a thing that said, don't panic. So that's fine. That should be fine. Overall, the mission was a great success anyway, even if the roster hit it. With several hundred exoplanet atmosphere probe, and again, we have trouble with the GTM to explain all of this. Damn stellar variability, again. But thanks to GWC, there were several tens of press releases announcing the discovery of an alien life for the very first time. Just like we did in the time of Kepler when we announced several times the very first planet in the habitable zone. Mm-hmm. Probably the same thing will happen with life. But honestly, that was just water. Finally, we renamed the mission concerned life to ETHZ, which stands for, I'm proud of that one. It's very good. Which stands for extraterrestrial planet in the habitable zone. Just for people who don't understand the joke. The PI of the mission life is at ETH Zurich. And
they are very good with the commercialization.
You can clap. Which was finally selected by ESA. And it's the first extrasolar astrobiology space mission. Cool. With the ETHZ, we will be able to probe the atmospheres of all the nearby Earth analog that's detected by the radiology survey and the old generation spectroscopic espresso. So that's cool. The mission is expected to be launched by Ariane 7 in the earliest 2060s. Finger crossed. And together with HW, which was also postponed because of Voldemort cut in budget of NASA, we should be able to unambiguously answer the question of the plurality of life, finally, by the end of this century, much before the end of the century. So I think we can say, hurrah, we are close to answer the question. And of course, this is recorded, so you will be able to go back if you are still able to have internet by 2039 and check again what I've said and check or not. We'll see. It's recorded now. So maybe I'm wrong, maybe I will be right. I will probably be wrong for some part. We will probably not rename life as ETH did. It will be fun, but anyway. So I'm going to my conclusions. For the second step. Of course, this was a bit funny, and I tried to put some humor in that, but also the idea of this prospective exercise was to explain to you what we should have within 15 years from now, unless I'm missing something completely unexpected, but this is what we should have by 15 years from now. So the good thing, even if we lost GWST because of Elon, is that the upcoming epochs, we are living the upcoming epoch of finding life elsewhere. We should be. And the exoplanet, we are going to live another golden age for exoplanets in astronomy. We have all this crazy and impressive instrumentation that will be launched over the next few decades to either find and characterize Earth analogs. This is PLATO, but also Espresso. I forgot to add Espresso because it's also one of the game player, and it will be tandem with PLATO to characterize this Earth analog. So we finally have, by the next decade, Earth analogs. We will probably find a few biomarkers in the atmosphere of some rocky exoplanets, either with the WST, REL, and the ELT as well. By the next decade. Actually, we are building the instrument for that. So at some point, we should be able to do that. And the search of life in the universe with HW and life, that again will tandem to get all those biomarkers that we need. We are already working on the mission that will be able to solve and to answer, or at least try to answer, the question of the plurality of life in the universe. I mean, like, remember at the beginning when I said that people like the Greek philosopher were already thinking about those questions 2,500 years ago. And we are the generation, you are the generation, maybe a bit too old, we'll see. But you are the generation that will be able to answer that question. Come on. I mean, like, this is one of the oldest questions of humankind, and you guys will be the one answering that question. That's great. Well, you have some work to do. Well, the next generation of astronomers, also known as you, will answer the question of life in the universe, unless our society collapses due to climate change or biodiversity loss. But we'll see. Let's hope that we can work as well to make all this great science as sustainable as possible, so that we can continue doing this great science in a sustainable way. Thank you.